All right, so the second half of section 4.2, maybe we can do a problem that's a little bit easier than the last one with the limit. So this is asking us to find the definite integral from -2 to 2 of the square root of 4 minus x squared. Now this is a semicircle. This is a half circle, and that's really all we need to know because it tells us that we can draw it from, so think about the domain of this from -2 to 2. Anything less than -2 or greater than 2 is going to give you a negative in your square root. When x is 0, the y value is 2. So again, I'm just considering what this function actually looks like graphically. And you know, it's at 1, what do you get? Square root of 3? Oh, like something like that. Not really super important to have some great graph. More important just to understand that this is a semicircle, half circle. That's great. Okay, so the point is the area of this we can think of geometrically speaking. That's all I'm trying to say. And we know that the area of any circle is pi r squared, so that the area of any half circle, semicircle, would be 1/2 pi r squared. And in our case, we can see that r is 2. So the answer to this is 1/2 pi times 2 squared, or 1/2 times pi times 4, or 2 pi. So the answer to this, and of course I've done something kind of weird here, but is with my spacing, but is 2 pi. That's all you have to think about with something like this, but understand that that is what that's asking, and that's the answer to it, because it's a nice thing that you can use your geometric skills to find. All right, a couple definitions here. Think about, we have the integral from a to a of a function. And if you think about that in terms of the limit of these rectangles, you basically, if you're going from a to a, your change in x, your delta x, thinking of the limit definition, is 0. So you actually cannot create rectangles or add up any of them. And so this area, not surprisingly, is just 0. So you can't integrate from a to a and get anything exciting. That area is 0. Now, if a is greater than b, then the integral from a to b is simply equivalent to negative integral b to a. So just the idea that we could switch the limits, and all that happens is that the answer is negative. So if you switch the limits, instead of going from a to b, you know, go from b to a. And that's because you're thinking of your delta x as being less than 0. So your delta x is being negative in that case. And so, for example, you know, if we were to do this, it would just be the integral, the negative of 1 to 4. And really, typically, we see a being smaller than b. It doesn't make a lot of sense for us to write it any other way. But that this is going to be negative what we got when we did this earlier from above. And this would be a negative of 12, or of course just negative 12. So it's just letting you know that if you switch the limits of integration, it's just the negative of if the limits aren't switched. All right, so a little bit more just thinking about the properties here. We've got the integral of a constant. So if you kind of go back to using the rectangles, you might see similarities there, but all we're thinking of is adding the area under a function that is constant. So you're thinking about like integrating, say, y equals 5, so the function 5, and if you integrate underneath that, well, you're going to have the height always being the same. It's going to be 5, and then you're going to have to multiply that height times the interval. Well, the interval is from a to b. So it's not surprising that this is always just the area of a rectangle, c being the height of that rectangle and b minus a being the width. The number 2 property is kind of handy because it allows us to take apart the integrals and add and subtract them from each other. So you can look at them as each piece if you want. In certain cases that might be handy, so they can be separated in that way. Here you've got that constant again. Not surprisingly, it can be pulled out, and you can multiply your end result by the constant later. And then with number 4, I want you to see that this is the integral, say, from a to b, and then you're doing the interval from b to c. And so not surprisingly, you can combine them and say that this is equivalent to a to c of f of x dx. So that's an important property. Number 5, says that if your function is always greater than or equal to 0 on some interval, then when you do integrate it, your answer is also always going to be greater than or equal to 0, because every y value is positive, and so of course the difference between those values and the x-axis are always going to be positive in terms of thinking about area. So you're going to have a positive value there. And this says that if your function is always greater than or equal to some other function on an interval, then the integral is, not surprisingly, always greater than or equal to the integral from a to b of g of x dx. So again, that's just, what you're saying is the y values are always higher on f of x than g of x. So of course, if those y values are higher, there's more area there that you're dealing with. And so when you integrate it, you're going to have more area on the f of x than the g of x along the same interval. Now for theorem 8, it tells us if your function is bounded. So you can think about, say you have some function from a to b, and it's, it starts here and it goes up here. So that just means it's always greater than or equal to m, and it's always less than or equal to big M on that interval. Then you can kind of think about this, the integral. So then when you integrate it, f of x on that interval, the idea is really just you can bound the answer for that area. So if you think about, maybe I'll use a different color here. If you think about this area, for example, here, okay, so that would be the area for the rectangle there with height m. And you do the same thing for big M. So for big M, it would be here. Sorry, that is not a great representation. That should be the same point right there. All the same point. Okay. Then you can see that the rectangle for big M is bigger than the function, and the rectangle for little m is smaller than the function. And so that idea can bound the function. And that's what theorem 8 says. So we've got, so that rectangle would have height little m times width b minus a. And the big rectangle would have height big M, and sorry if that's not looks enough like the big M, times b minus a. So that's theorem number 8, that you can bound a function if it is bounded along an interval like that. So let's take a look and use a few of these properties. You're welcome to pause it and see what you can do with these, and then come back and watch what I do with these. But I'm just using the properties from above, being given this piece of information, this piece of information, and this piece of information. Okay, so what I'm going to do is I'm first using property number, I have them listed here, property number 2. I'm going to separate these, and I'm going to bring this 2 to the outside. So I'm going to have 2 f of x dx. Bringing the 2 outside is number 3 because it's a constant. And then I'm also going to have this other integral 2 to 5 of g of x dx. So again, I'm just using the idea of the properties here to separate this. And then we know what the integral from 2 to 5 of f of x dx is. It gives us it right here and says that it's 6. So that's just going to be 2 times 6. And then the integral from 2 to 5 of g of x dx is given to us as well. That's 3. And then we add them together, and our answer is just 15. That's all we're being asked to do there. For b, we want the integral from 3 to 5 of f of x dx. Now we don't know 3 to 5. We know 2 to 5, and we know 2 to 3. So think about that we know 2 to 3, and we know 2 to 5. So we're given that the area, of the function, whatever it is under the curve, from 2 to 3 is 2, and we know that from 2 to 5, it's 6. So you can probably already take a guess and understand that this is actually coming from a number 4. It's just instead of an addition, it's the subtraction of it, the idea of taking away the area that you don't want. So this is going to be from 2 to 5 of f of x dx, but we're going to have to subtract that integral from 3 to 5, from 2 to 3 of f of x dx. And that's going to give us the 6 minus the 2, and we get 4. So again, just using what the properties are equal to. I don't know if you noticed, but today I'm wearing my Pasadena City College shirt representing Pasadena City College. So remember that for the video. And the last thing I'll mention here is we're going to show, again, using the idea of these properties, that we can bound that integral that you see there, the square root of x cubed plus 1, from 0 to 2. And we're going to try to show that it is greater than or equal to 2 and less than or equal to 6. So I think I'm going to need a little more space than I might have available to me at the bottom of the slide. But I think I can go right here. So I'm going to start with x. And what I want you to notice is that x goes from 0 to 2. So we know that x goes from 0 to 2. All right. And basically what I'm going to try to do in the middle is I'm going to try to create the square root of x cubed plus 1 by doing whatever I do to all 3 sides here, the middle and the 2 sides. So the next thing I'm going to do is create x cubed, and so that means I'm cubing all 3 sides. So that gives me this. Then in my little square root, I have x cubed plus 1, so I'm going to need to add 1, and that's going to give me 9 here. Okay. Then I can take the square root, because that's what I need to do to get x cubed plus 1 here, square root of, and so that's going to give me 1 here, and that's going to give me 3 here. However, we're not done, because now we need to integrate from 0 to 2. So hopefully I have enough space here. I just need like 2 more lines. So I'm going to integrate from 0 to 2 and x cubed plus 1. And what I want you to listen to here, because this is what it is. Remember, when we integrate just a constant, so this is coming back to property number 1, so take a look at property number 1 on your page. When you integrate a constant over some interval, the answer to that is just the constant times the interval, in this case 2 minus 0. Over here, it's 3 times 2 minus 0, because you're just integrating basically a straight line that has a height of 1 and a height of 3. So that tells us that we have 2 less than or equal to 0 to 2 square root x cubed plus 1 less than or equal to 6. And that's what we're asked to show. So we are done. You can make a note here. I notice it on my notes. These are the limits of integration. That's just where those came from, in case anyone's like, how did we decide 0 to 2? Remember, that came from over here. So that is section 4.2.